Y'all ready for math? Y'all ready for math? Welcome back to another pre-calculus honors virtual instruction video. Let's rock and roll here. Get a little star action going, dive right into it. Star! And get a little recall action going. Recall. We've been talking about the indefinite integral, okay, basic integration for this, take-home assignment that you're actually going to have assigned tomorrow. This is Wednesday's video. Thursday, you guys be working on review ditto, okay, and I'll also assign the take-home exam. You also have Friday to work on it as well. Good luck on your APs next week, okay? This table's made of wood. Knock on wood, okay, for you guys. You're all going to do wonderful out there. Make sure you, have your e-ticket all ready, okay? You're communicating with the College Board. Make sure you know how to upload responses and stuff like that. Sure your teachers have been going over that with you, but you can really read that testing guide. You want to practice it with that demo they gave you. But enough about AP. Let's talk about pre-AP. We're talking about the indefinite integral. Let's just recall those 5 basic rules. The integral of u to the m with respect to u. That's u to the quantity m plus 1 divided by m plus 1 plus c. N can equal -1. Remember, we also had that list of famous u's. Famous u's. Yoo-hoo! All right, and if something is not one single letter raised to a numerical exponent, you could force it to be one single letter raised to a numerical exponent by setting u equal to the base of a numerical exponent. Okay, so the base of a numerical exponent. Then we talked about trig, okay, the integral of sine u with respect to u. Remember, sine is the bad guy in the world of integrals, so negative cosu plus c. All right, and then we did the integral of cosine u, cosu, with respect to u. He's the good guy in the world of integrals, so sine u plus c, c do. And if you have sine or cosine alone in an integral, and the argument is not one single letter, you can force it to be one single letter by setting it equal to u. So the argument of a trig function, pretty famous u, argument of a trig function, the argument of a twig function. I really need to cut my nails, by the way, okay? So when you actually look at them in this video, don't make fun of me too much, okay? Definitely I could use a little bit of, a nail clipping, all right? But it's quarantine, right? I haven't shaved in 2 weeks. Just kidding. I shaved yesterday. I was looking like a woolly mammoth. I was like, you got to shave there, Berto. It's a good thing we still have faculty meetings and math meetings online. It's really the only reason I shave anymore. Then we talked about yesterday the integral of e to the u with respect to u, okay, so as far as the integral of e to the u, remember, as long as it's e raised to one single letter, you could say the answer is e to the u plus c, but it has to be raised to one single letter. Don't be telling me the integral of e to the 2x is e to the 2x plus c. That's not correct, okay? So basically, if you see e inside an integral, set u equal to the exponent of e. I'm not saying it works 100% of the time, but it works like 95% of the time. And now finally, the last one we're going to get more into today, the more complicated types of situations. If you have the integral of 1 over u, so basically if you want to integrate a quotient and the bottom's only being raised to the first power, we say ln absolute value u plus c. But things are a lot more involved, and we're going to talk more about this one today. The u substitution situation specifically. There's a cool little trick you could use, so you don't need to use u substitution. We'll do it both ways. Anyway, so we don't really have another, one to put right here, because we're going to talk about things a little bit differently today with this guy. So really what we're doing today, it's really integration of transcendental functions, day 2, if you want to put it that way. We'll do number 14 from the homework real quick, because number 14, we talked about in the last video, we never integrate ln in this class, okay? And people are like, well, why are they giving me an ln here, if I have to integrate it? Well, look, first off, is it a basic integration situation? There's no way, okay? There's division going on here. You have the base of a numerical exponent not equal to one single x. And if it's not basic integration, you could try to manipulate, but what do? Just double bubble ln x here. It's not really going to get you anywhere. So why not pick a u and go with it? And I really think there's only one viable u here, okay? I really think ln x is the only viable u. That's the base of a numerical exponent, okay? It's really the only u that's represented up here. And people are like, yeah, but Berto, this x down here has to go away. But if you're thinking the derivative of ln x is 1 over x, and that derivative is normally generated downstairs, okay? If you have a 1 over x downstairs, that's going to be the same thing as multiplying by an x upstairs, okay? It's going to cancel out with this x right there. You might want to be thinking like that. You don't need to be, okay? You could just dive into it and be like, all right, so du over the derivative of u, we know the derivative of ln x is 1 over x is equal to dx, but only Claffey would divide by 1 over x. The rest of us would multiply by x. It's actually pretty simple over there. And now, it's funny. They call it u substitution. I think they should call it 2 substitution. Very good. Now it's u squared times, take out that dx, replace it with an x du, leave this x downstairs. Look at the lusciousness commence here, okay? The x's are going to cancel out, and you forced a wonderful basic rule. Just the integral of u squared with respect to u, okay? And we know how to do that. Add 1 to the exponent, divide by that number, add some crustaceans, lobster, and here we get 1/3 u to the 3rd power, so ln x quantity cubed plus c. Not really a bad problem, but there are going to be weird things that happen with integrals. You just got to play around, pick a u, and just go with it. Hopefully the rest of that homework was not the most horrible thing in the world, okay? Something like number 1, easy, pull that constant to the side. Integral of e to the x is just e to the x plus c. Over here, even though e is not raised to one single letter, it is true that you just get back what you integrated, but that's only because the derivative of the inside was equal to 1. Don't be telling me over here the integral of e to the negative x is equal to e to the negative x plus c. That's not one single letter. Okay, negative x. You got to set it equal to u, and dx is not equal to du like it was in the previous problem. Here, du over negative 1 is equal to dx. That's why it's negative e to the negative x plus c. So be careful, okay? Something like number 5 is kind of cool because there's a quotient here. We'll deal more with integrating quotients today, but here, if you bring this upstairs, negate his exponent, e to the negative x cubed, now you can set u equal to e's exponent, and things work out pretty nicely. Number 6 always bothers people because you got to set u equal to radical y, or y to the 1/2. Remember, the way I have it set up here, you should be able to go right from this step to this step. I kind of put the step in between to cross multiply, but maybe you just have this, u equals radical y. Du over the derivative of u is going to be equal to dy in this case. Remember, if it was radical x, the derivative would be 1 over 2 radical x. Radical y, the derivative is 1 over 2 rad y. And only Rourke would divide by 1 over 2 rad y. The rest of us will multiply by 2 rad y. It's supposed to be du here, equal to dy. And that's how I end up with this guy right here. So now it's not as bad as you might think. It's not really the calculus. It's always the algebra that bothers people with stuff like this. This one, we did a similar one in class, so hopefully not too terrible. Number 10, classic many over 1 type of situation. Be ready for that. Very popular on my exams. Popular on the AP too, okay? It does show up every now and then, and 14 is a problem that we just did. You might be like, what the heck are these problems over here? That's what we're doing today. You'll have homework on it tonight, and then more practice. No video tomorrow. It's just, you guys have the homework solution. You can work on it, and then you'll work on the review ditto and check your work. But if you're struggling, let me know. Send me a reminder, something like that, an email. I've been helping several kids out virtually like that. It's easier than you might think. Coffee, my own, my precious. Okay, so send me, an email or a remind if you want to talk about something. Today, we're really doing integration of transcendental functions, day 2. And let's integrate something like this, okay? And it looks so harmless and innocent. You're like, look at this beautiful thing over here. What the heck do I do? Okay, it's not basic integration, okay? Because I see division going on here. You could be like, oh, the argument of a function is not one single x. You're right, but you might not even know what the outside function is. It's actually 1 over x, believe it or not, here. Most people wouldn't realize that. Remember, if you don't know how to integrate something, if it's not basic integration, which I don't think this is, I see division right there, pick a u, okay? And here's the thing. There's only one viable u for this problem. I can't imagine what you would set u equal to besides 2x plus 3. It's kind of weird, though, because the 2x plus 3 is only raised to the 1st power. Certainly, if that was 2x plus 3 quantity squared, you would definitely set 2x plus 3 equal to u, and you'd bring it upstairs, and you have u to the negative 2. We've done problems like that. That's the classic type of u substitution situation we started with. This one's weird, though. You could bring it up, but you don't need to, okay? If you bring it up, it might actually cause some confusion. Remember, du over the derivative of u is going to be equal to dx. So du over 2 is going to be equal to dx. Sometimes you don't know where an integral is going. You just got to dive in and go with it. Go on like a magical quest. What's going to happen here? So here I have 2. Downstairs I now have u to the 1st. Take out the dx, replace them with a du over 2. You might be like, oh, great. What the heck happened? What is this? Well, you might notice the 2's now cancel. And think about what you're left with. Okay, now you're left with the integral of 1 over u with respect to u. And that's a basic rule. We know the integral of 1 over u with respect to u is ln absolute value u plus c. And we know that's really ln absolute value of that quantity 2x plus 3 plus c. And that's my answer right there. So if you want to integrate a quotient and the bottom isn't being raised to a power, a visible power, which means just being raised to the first. It's actually an ln type of situation. You could set the denominator equal to u, but there's actually a much cooler way to do it. And you probably won't like it at first, okay? And you don't need to do it at first, but it's going to become extremely useful. It's a little trick for these types of problems. It's really mental integration, but it's like a controlled mental integration, so it's not exactly mental integration. But here's what you could do. If you want to integrate a quotient and the bottom isn't being raised to a power, other than 1, take the derivative of the bottom. If you take the deriv of 2x plus 3, you get 2 back. And you might notice, do you see how that 2 is the numerator? So if you want to integrate a quotient, the bottom's not being raised to a power. If you take the derivative of the bottom and it perfectly matches the top, the answer is always going to be ln absolute value of the denominator plus c. Every single time. If you take the derivative of the bottom and it matches the top, ln absolute value of the denominator plus c. Remember, it only works when the bottom's raised to the first power. So a lot of times we say it's not being raised to a power, even though technically it's being raised to the first. Really, this is a shortcut for this rule here. The integral of 1 over u with respect to u. So here we got the shortcut. I think it's worthy of one of these. What is that? Everybody at home right now, yell it out. So your parents can be like, what's going on in your room? Megastar! Okay, if you want to integrate a quotient, and you see that downstairs, you see a function, we'll call it f of x, because who knows what the heck it's going to be. The derivative of f of x is f prime of x. If you see that derivative upstairs, so that's this situation here, okay? F of x is 2x plus 3. F prime of x would be 2, okay? If you want to integrate a quotient, bottom's not being raised to the power, and the derivative of the bottom is up top. It's always going to be ln absolute value of the denominator plus c every single time. And you might not like that trick now, but man, it's going to become incredibly useful, okay? Especially when you get to differential equations and just in general, it can be nice to mentally integrate, but it can also be difficult. But this is a controlled mental integration. Even in situations where the derivative downstairs doesn't perfectly match the top, you can still use the trick in certain situations. In AB, you might be able to get away for the whole course without using this trick and just doing this. But really, even in AB, you should be able to do this. It's not bad if you practice it. So really do it either way. You should really do it both ways, this year. And try to get comfortable with this way, even though you don't like it. BC, by the way, you should be able to do this, okay? End this. It shouldn't be an issue. Let's do this over here. If you're integrating a quotient, bottom's not being raised to a power, it's an ln situation. One way is to just set the denominator equal to u. All right, and that means du over the derivative of u, which is 5 in this case, is going to be dx. Okay, and now we can just do this, the traditional way, the integral of, now it's 3 over u times du over 5. So a little bit different from the last problem. The last problem, the 'two's canceled out, and you were just left with 1 over 2, 1 over u. Here, the 3 and the 5 doesn't cancel out, but that's okay. They're both constants connected by multiplication. I could bring them out. This is a 3. This is actually not a 5. This is a 1/5. You're really bringing a 3/5 out to the side. 3/5 times the integral of 1 over u with respect to u. Then you force the basic rule. It's a pretty easy situation here. 3/5 ln absolute value of u plus c. And that means 3/5 ln absolute value of 5x plus 6 plus c, okay? But you should use the trick here, okay? It's very useful. If you want to integrate a quotient, the bottom's not being raised to a power, try to take the derivative of the bottom. And you can see the derivative of the bottom is equal to 5. Now, that derivative does not perfectly match the top, but the idea is this. As long as you can take the derivative of the bottom and multiply it by some constant to get it to match the top, you can still do this, okay? And people are like, well, 5 times what is equal to 3? Whenever you want to create another constant using a constant by multiplication, you could always do that, okay? You could always figure out a constant to multiply a constant by to get another constant. Like, it's weird, okay? But, suppose I wanted to... suppose I started with 16 and I wanted to multiply it by some constant to get 117. Who knows anything about numbers? Shouldn't have even said that because you can't even see it. Now you can. So imagine you want to do 16 times some constant will give you 117. People are like, I don't know what the constant is. My name is not Harrington. It's actually very easy. Just 117 over 16, right? Because these will actually cancel out, give you that 1/17. So you could always multiply a constant by another constant to generate any particular constant. So you want to think, is there any way I can create the top? I can multiply the derivative of the bottom by some constant to create the top. And you can. 5 times what equals 3? 5 times 3/5 is equal to 3. Take that 3/5, write it down, and then put ln absolute value of the denominator plus c, just like we did before. So if you want to integrate a quotient, the bottom is not being raised to a power. If you take the derivative of the bottom and you can multiply it by some constant to create the top, put the constant down, write ln, the absolute value of the denominator, plus c. Works every time. It's a very useful technique. You just have to make sure you multiply by a constant. You know, if there was a 3x up top, there's no way you can multiply 5 by a constant to get a 3x. You need to multiply by 3x over 5, and this right here is not a constant. Okay, and stuff like that's going to become important, okay? And it's important now. You know, some people do this. They just think about the derivative of the bottom is 5, and they pull that 5 to the side, that 1/5 with the 3. They pull the 3/5 to the side, then do ln absolute value of the denominator. That's what's going on here. The trick is really just a controlled u substitution. You're taking the derivative of the bottom, just like here. The derivative of the bottom is always going to be generated downstairs. It's the same thing, this 5 down here and this 5 right here. But this is quicker, because if this was the integral of 3 over the quantity 5x plus 6 plus x squared minus sine x, you need to split it into several integrals and then actually worry about a u substitution for this singular one, because the u wouldn't apply to the other functions. So it's more important than you might think. You know, this guy over here, same deal, right? Integrating a quotient, the bottom's not being raised to a power. If the bottom was being raised to the 5th or something like that, or square rooted, you'd bring it upstairs with a negative exponent and set u equal to the base of the numerical exponent. That's old problems by now. But even here, you could use u substitution. If, you know, you're integrating a quotient, the bottom's not being raised to a power, set u equal to the bottom. I really think it's the only viable u here anyway. So this still works. Remember, if you're struggling with, you know, the trick, do it this way first, but try to do the trick, okay? The trick, you know, you can get away with doing, you know, this assignment you'll have coming up that's due Friday without the trick, I'm sure. But the trick, very useful and something I want you to think about. So here, perform our two substitutions, 2x over u times, now we have du over 6x. Think how important this is. This is different from the other problems. We just had constants up top. Now we have that variable x up top. But since there's an x squared downstairs, when you take his derivative and he's generated downstairs, those x's are going to cancel out. Pull the 2/6 out to the side, and now it's 2/6 integral of 1 over u with respect to u, which is really 1/3 ln absolute value u plus c, which is really 1/3 ln absolute value of 3x squared minus 5 plus c. And really, you could skip a bunch of these steps. You can go right from here to the answer if you're good. And also if you're good, and really all of you can do this, do the trick, okay? If you want to integrate a quotient and the bottom's not being raised to a power, take the derivative of the bottom, which here we know it's equal to 6x. And think about it. As long as you could take that derivative and multiply it by some constant to create the top, you could use the trick. And remember, it's a constant, and the x's match up here, which is nice, okay? Because now you could actually just multiply this thing by what? 2/6. Okay, and now you can see the 6's will actually cancel out. 2 times x will be equal to 2x. So we take that 2/6, then we write ln, absolute value of the denominator, plus c. And yeah, you know, you probably want to make that 2/6 the 1/3, but regardless, we know it's equivalent to this down here. Not really a bad problem, okay? You know, some people even do this. There's a student I taught years ago, Caitlin Chiodo, her sister, Allison Chiodo. Alice, why did I say Allison? Oh, if she watches this video, she'll be very mad. Alice Chiodo graduated a couple years ago. The Caitlin Chiodo method, where she was like, Berto, you know what? I just look at this 6x down here, and I look at the 2x up top, and I think about canceling the x's and pulling the 2/6 to the side. There's nothing wrong with that, okay? It's the same thing as what we're doing over here, but sometimes that can actually get a little wonky, believe it or not. So try to think about multiplying the derivative by a constant to create the top. And if you can, write that constant down, then do ln absolute value of the denominator plus c. You could actually also just set the denominator equal to u if you want to, okay? But try to do the trick, because things start getting extra cool. Like, people look at this problem right here and they're like, what the heck is going on? Like, this is so ugly looking. Or other people are like, oh, it's so pretty. I feel pretty. Oh, so pretty. It's a very easy integral. You know, here you're integrating a quotient. The bottom's not being raised to a power. So why not just take the derivative of the bottom? And geez, what's the derivative of e to the x plus 2? How about e to the x plus 0, which is just e to the x? OMG, that's upstairs, okay? You don't have to multiply it by a constant to create the top. So that's just ln absolute value of the denominator plus c. You could multiply it by a constant. You know, the derivative of the bottom is e to the x. What constant do you multiply it by to create the top? Well, 1, okay? So you could put a 1 right here if you want to. ln absolute value of the denominator plus c. They might actually have this in multiple choice. They might actually have, you can also set u equal to the denominator as well. It'll work. Try that in your own if you want to. They might just have ln of the quantity e to the x plus 2 plus c. then people freak out. They're like, Berto, I thought you need to have this absolute value. You know, what if they have this one and this one? They won't have both, okay? They'll have one or the other. But you're able to do this because if you think about what y equals e to the x plus 2 looks like when you graph it, people are like, I don't know what it looks like if you graph it without a calculator. Then don't take AP Calculus. We talked about stuff like this. You should know y equals e to the x, we know looks like this. Nice little exponential increase. But now it's shifted up by 2 units. So it looks like a little something like that. Really horrible graph that I just drew right there. But the idea is that this thing, you know, it has a horizontal asymptote at y equals 2. Because normally it'd have a horizontal asymptote at y equals 0. Just notice, domain all real numbers, function always represents y values. And you'll see that all the y values are always positive. So e to the x plus 2 is always positive. It's not necessary to take its square root. You could just put the parentheses there. So something to think about. There's always more than meets the eye going on with problems, okay? So, you know, some things to play around with. Just like this, you know, I know I've been getting the emails, the reminds from people. They're like, Berto, we did the integral of sine u, the integral of cosine u, and now I can't sleep. I'm tossing and turning in my bed at night because we never did the integral of tan u, or the more easy version, the integral of tan x. This right here is actually an ln. That's why we haven't done it yet. This is the integral of, we can write as sine x over cosine x, can't we? Can't we? Can't we? And believe it or not, now Now you're integrating a quotient. The bottom's not being raised to a power. Take the derivative of the bottom. Just be careful. Some people are like, oh, cosine's the good guy. He's realized the error of his way. No, okay, this is a derivative. He's a bad guy in the world of derivatives. Make sure you know what world you're in. Here we have negative sine x. Why did I put u down there? Berto's losing his mind. This is what happens if you wake up in the morning and drink coffee and no water. All right, so let's take the derivative of the bottom. Derivative of cosine x is negative sine x. Now notice, that derivative is not chilling up top, but you can multiply the derivative of the bottom by a constant to create the top. What constant would you multiply by? I'd multiply by -1. So the answer is going to be -1 times ln absolute value of the denominator plus c. Remember, it's not necessary to put -1 there. You can just put a negative. So that's the integral of tangent. And here's where things get a little bit more filthy, okay? Because if you open up a calculus textbook, if you just Google online what's the integral of tangent, you won't see this. This is not the formula that they often show. They often do this, okay? Remember with an ln, if you have, I don't know, the ln of like x squared, something like that, if the argument of an ln is raised to a power, you could take that power, drop it like it's hot. The original drop it like it's hot, connected to the front of the ln by multiplication. But don't forget, if you have anything connected to an ln by multiplication, you could put it back up like it's cold, right? Make it an argument of the, an exponent of the argument. That's what we're going to do here. We're going to take this -1. We're going to make it an exponent of cosine x. So ln absolute value of cosine x, quantity to the -1. Don't put cosine with the -1 in the middle of x, because that'd be cosine inverse of x. That's not cosine of x quantity to the -1. Cosine x quantity to the -1 is the same thing as 1 over cosine x quantity to the +1, right? Okay, getting rid of the negative exponent. And 1 over cosine x, we know is really equal to secant x. So this is what they'll be looking for in multiple choice. And that bothers some people. So a lot of people just like to memorize this. Star! New rule. I wouldn't worry about so much for this test coming up, but things like this do show up on the AP exam every now and then. The integral of tan u is actually ln absolute value secant u plus c. Okay, remember, you might actually have to say u, you know, equal to something, okay? If it's not one single letter, that's the argument of tangent. So try not to go crazy with stuff like this, but that's why we didn't talk about it, because the integral of tangent is an ln. The integral of cotangent, believe it or not, is part of your homework. The integral of cotangent x with respect to x, well, that's the same thing as the integral of cosine x over sine x with respect to x. I think that's what it says on your homework. But remember, that's really the integral of cotangent, okay? So not that you really need to memorize this. Cotangent is a lot easier, by the way, because the derivative of the bottom perfectly matches the top. So it's the perfect ln trick. Doing some of your homework right there. This one's more annoying because of the algebra here. A little antiquated. I wouldn't worry about it so much anymore. But just something to think about, okay? You know, and then maybe just one little thing here to end with. You know, it's really the end of the topic there, right? So make sure you know your basic rules. Where are my basic rules? Your basic rules. Make sure you don't just know U substitution, but also your basic integration. Don't forget those problems we did the first and the second day. The review ditto has some cute problems with some problems. People try U substitution and it gets you nowhere. And all you need to do is like distribute, and it becomes extremely easy to actually, you know, get the answer. So make sure you're on the lookout for stuff like that. Maybe end things up with a little comic here. Give you time to read that. Come on, tell me that's not hilarious, okay? You know, why don't you integrate yourself into the party, e to the x? Why bother? It won't make any difference. If you don't know why, it won't make any difference. You've not been doing your work, okay? Get in touch with me if you need to. Once again, last video for a while, okay? You know, Thursday and Friday. Thursday working on the review ditto, Friday working on the assignment. Then 2 weeks of AP is going to be real light, okay, as far as in here is concerned. But after that, we're rocking, we're rolling, folks, okay? So good luck on all your APs. Good luck out there. I hope you're doing well, okay? You know, the summer, I think, is going to be different than most summers that we're used to. But in the end, everything will be back to normal. It's just going to take a while, okay, before it's true. But hopefully I do see you guys before the end of the year. I don't know if that's going to happen, though. But hopefully next year I'll be able to see you guys. So, you know, we'll see what happens. It's kind of, you know, makes you a little anxious not knowing what's going to happen. But we'll be okay. Okay, we'll persevere. And we'll see each other soon enough. And you'll be looking at me and you'll be like, God, I wish I was on quarantine again because I can't stand being in this classroom. Just kidding. Anyway, this is Berto signing out. So everybody have a safe and healthy and a happy. And we'll see you soon. Adios.